All right, welcome back to generative deep learning. Just want to re-emphasize what we're doing. So we have a data set, and the data is coming from a certain distribution, and we don't know that distribution P of x. So the data can be text, can be images, can be music. Yeah? So what we're gonna do first is we're gonna learn a latent space Z. It's gonna be lower dimensional, and so that we have a model that we can sample from and generate new data that is similar to this data. That is the whole concept. Yeah. So before we talk about variational autoencoders, which we're going to apply to images, we have a few concepts that we need to cover. One concept is autoencoders, so we've not seen this up to this point. And then we're going to have another intermezzo where we're going to define information content, entropy, cross-entropy, and KL divergence. This we've already covered in the previous videos, 115 to 190. And I said at that point that it was an option. So we're just going to refresh quickly what we have discussed in these videos. So the first thing that we do is let's look at autoencoders. Now, what is an autoencoder? Well, it's quite simple. You have input data of dimension D, and then you're going to encode. Yeah, so you're going to basically transform that input data into a Z space, and that Z space is a lower dimensional latent space. Lower dimensional, that means that in this case P is smaller than D. So basically what you do is you compress your data and you keep the features that are relevant. Yeah. Now there's also autoencoders where D is larger than P. Yeah. But this we do not use for this problem. Remember, we've also covered this a little bit when we discussed word2vec. Remember videos 219 to 221, we discussed a continuous bag of words and skipgram, and we tried to predict the next word. So that in that case we also did that. So we went from a word to a latent space, and in this case we call this word embeddings. Remember, you had this graph, so and words were represented as vectors, and similar words clustered together. Remember that we said that if you have king and you subtract the man vector and you add the woman vector, then you will be very close to the queen vector. Alright, so but in this case of autoencoders, the only difference with what we did here is that we want to reconstruct the input. So here we wanted to predict the next word. Yeah? So the input and the output were different, but here the input and the output are the same. Yeah? And again, the output has dimension D. So we encode and we decode. Alright? Now what is the objective function? Well, it's quite simple, right? You take the minimum between these two and you square. Yeah? So you look at the difference between these two vectors and see what the cost is. So there's another way to write this. In this way, you have an input x, you encode. Yeah? So you're gonna transform x to a latent space, and we're gonna do this using a neural network with activation ReLU. So then here you have your latent space, and this latent space gives you the features. Yeah? And then we decode, and a decoder here is again a neural network with ReLU, and you end up at your reconstructed input. So this is an autoencoder. It's very simple. Input, compress, and then reconstruct the input.